Okay, so this is the second video on second order differential equations. In the first video we looked at a very specific set of second order differential equations where we had this same left hand side that's written here, so a d2y dx squared, a dy dx, and a y with some coefficients, some numbers in front of them, but we had it equal to 0. So in this video we're going to generalise slightly and have it equal to a function of x rather than equal to 0. In FP2, the function of x actually, there's only a few types you're allowed. I think it's about 6 different types that that we have to learn about. One of those is something like 4x, a linear term. But we're not going to talk today too much about the different types. We're going to save that for the next video. What I'm going to do now is go through an example to show you this kind of like what we're aiming for in the end. So in this example, we're going to try and find what's called the general solution of this differential equation here. And it's going to be a little bit mysterious, this example, because I'm going to do some things, I'm going to make some choices that I'm not going to be able to fully justify or explain at this point. But I think it's better for you to see a full example, see what you're aiming for, and then me to go back in another video and explain to you, well, how do you do this bit here, or why do I make that choice, rather than telling you what choices to make before you've seen anything that you'll be choosing to do. So I think this is the better way around. But this does mean that you have to sort of bear with me a little bit, because certain aspects you're not going to know why I'm doing that yet. But just bear with me, because it will become clear once you've seen these two videos. Okay, I think that's enough of rambling. Let's get on with it. So there's two parts to solving this kind of equation. So the first part is called finding the complementary function. Or the CF, if you like. Saves you writing out complementary functions now. So what we do here is take the same differential equation up there. In fact, we write down the left-hand side in exactly the same way as written up there. But we change this side to 0. No matter what it is there, we make it equal to 0. Which seems odd, which seems strange. But what's good is that we can solve these kind of equations, because this is what we're doing about in the last video. We know we can let y equal to e to the mx, and then we know that means that when we differentiate it, we get m e to the mx, and then differentiate it again, we get m squared e to the mx. And we know if we plug these things in here and divide through by e to the mx, we get something that looks a bit like this. And then we think, can we factorise this? Has it got real roots, or do we need to use the formula? I think we can find two numbers at times together to give 6, or minus 6, sorry. Add to give minus 1. I believe that is 2 and minus 3. Yep. So that gives us two real roots, two distinct roots, minus 2 and 3. And so we have to think again now, what is the form of the solution? I think it's a e to the minus 2x plus b e to the 3x for two real roots. Now this thing here, this is called the complementary function, and it's not the solution to this equation, it's the solution to this one, but it turns out that we need this solution to solve this more general, slightly harder version. So we've got that bit, we've done half of it, now we've got to do the other half. Now you see, the reason this isn't the solution to this is because if you take this y and you differentiate it, and you differentiate it again, and you shove it in here, those substitutions that you get, you'll find out that the second differential minus the first differential minus 6 lots of this, it will turn out to be equal to 0, not equal to 4x. So what we need is a y value, or a y function, that solves this equation so that when we plug those numbers in there, we get 4x. And that thing is called the particular integral. It's the value of, or the function of y that can you plug in here and get 4x. Particular integral. I can't spell while I'm talking. Sorry. Now this is a bit where it gets a bit mysterious, because I'm going to choose a value for y. I'm going to choose a function. There it is. So I'm going to say let y equal lambda x plus mu. And what I'm going to try and do is work out what lambda is and what mu are by doing the following method. Now, what I don't want you to do is worry about where this has come from, because I'm going to have to tell you, based on what function here, that depends what particular integral you pick here. And there's about 6 types to learn, and it will make some more sense when we talk about it next time. So this is the bit where I'm saying, just go with me, okay? The point is, though, I'm going to try and find out what these lambda and mu are. So to do that, I'm going to differentiate it to work out what dy dx is. So differential of lambda x is lambda, differential of mu is 0. These are like constant numbers that measure like 2x plus 4 or something. The x goes away. Then we differentiate again. The constant number becomes a 0. The reason we're doing that is because we can now substitute these things into this equation over here. So for the d2y dx squared, I'm putting in 0. Then we do minus dy dx, which is lambda. Then we're going to do minus 6 lots of y, which is lambda x plus mu. And that's going to be equal to 4x. So here it was equal to 0 to work out the complementary function, but now we're working out the particular solution we want, so we're using the 4x. Let's just tie this up, expand it out. We've got minus lambda, we've got minus 6 times lambda x, we've got minus 6 times mu, that's equal to 4x. So here I've got my x term, and then I've got my constant term. Here I've just got an x term. To work out what lambda is and mu is, we're going to do something called comparing coefficients, which you've probably come across before. So we can compare the x coefficient and go to this bit here. This minus 6 lambda must be equal to the x coefficient over here. So minus 6 lambda must be 4. And then this bit here, the constant term, must equal the constant term here, which must be 0. So we must know that minus lambda minus 6 mu is 0. And now we've got ourselves some simultaneous equations to solve. But this one's very straightforward. We can solve that easily. We just do lambda divided by minus 6. So we've got 4 divided by minus 6, which I think is minus 2/3. Feel free to use a calculator. Then we can plug that back into here. Minus 2/3, which is what lambda is. Minus 6 mu is equal to 0. So 2 minuses makes that 2/3. Move this to the other side. And now divide by 6, we get that mu is equal to 1/9. Again, feel free to use a calculator. There's no bonus points doing it in your head. So by doing this, by differentiating your y and plugging it back into here, we've found that if we have lambda equal to minus 2/3 and mu equal to 1/9, then this y, lambda is minus 2/3, x, mu is plus 1/9. This y here, we plug that into there, we get it's equal to 4x. This is a particular integral. This is a pi. Now, the problem is there's actually probably other choices for the y we could have made. I mean, I guessed at this, we solved it and it worked, but this is only one solution, and we want to find the general solution. Not just one solution, but the format that any solution we could ever want to have would occupy. And that's what this thing over here is. You see that these terms a and b, these unknowns, we can make a and b anything, a 2, a minus 1, a 0. If we put on the end of this function, we'd still get it equal to 4x, because when you differentiate this one, you get 0. So this is like the kind of plus c when you integrate. You've got a plus c on the end because you don't know what the plus c might be. Here, the plus c isn't just a constant value. The plus c of this one is this complementary function. So the general solution is given by the particular integral, minus 2/3 x plus 1/9, added to the complementary function, a e to the minus 2x plus b e to the 3x. This is what gives you the 4x. This is what makes it general. It's a bit like when you add the plus c on the end, you see what I mean? Okay, in the next video, we're going to talk about how we get these particular integrals. How do we do that for different functions of x that we might see? Once we've done that, we should have to solve any second order differential equation. See you next time.